Welcome to the pod Biomanufacturing and Fermentation Technology. In this episode, we translate microbial science, process engineering, and manufacturing realities into insights that scale.
Welcome in, everyone. If you're joining us for this deep dive today, you likely have that drive to strip away the noise.
Right, getting straight to the mechanics of things.
Exactly. You want to see how complex systems actually work. Looking for those structural insights that you can apply across entirely different disciplines without getting bogged down by endless fluff. So our mission today is to take a highly concentrated technical brief and extract the architectural logic right out of it.
And the specific source material we are examining today, it offers a really remarkable look at industrial problem solving.
Yeah, it really does.
It's this highly focused engineering blueprint that addresses a severe bottleneck in industrial biotechnology. And the stated objective is, well, it's straightforward, but mechanically daunting.
Which is?
To eliminate oxygen limitation in high-viscosity fungal or actinomycete fermentations.
Right, and I know that might sound incredibly niche to some of you, but the framework it provides for overhauling a failing system it's universal.
Oh, absolutely.
The brief outlines a targeted solution kit designed to be fully implemented in just 7 to 10 days.
Which is incredibly fast for this scale.
Exactly. We are talking about fundamentally altering the physical and thermodynamic properties of a massive industrial environment in barely over a week. And to ground us, let's picture the scale we are dealing with here.
Yeah, you really have to visualize it.
Right, because these aren't tabletop lab flasks you see in high school chemistry. We are talking about multi-story stainless steel bioreactors holding tens of thousands of gallons of biological material.
Scale is the defining variable here. The laws of physics they behave very differently when you're trying to manipulate fluids and gases at that sheer volume.
Yeah.
The problems identified in this blueprint and the interventions it dictates are entirely driven by the physical limitations of moving material within that massive enclosed geometry.
Okay, let's unpack this. The brief identifies the specific operational environment causing the failure, right? It says fungal or actinomycete fermentations that have reached a state of high viscosity.
Now, anyone familiar with industrial fermentation knows we are not dealing with a simple watery broth here. But let's clarify the biological actors causing this physical shift. What are we actually looking at?
Well, for those who might need a quick refresher on the microbiology, actinomycetes are essentially a group of bacteria that exhibit fungal-like growth.
Okay.
So both fungi and actinomycetes develop these complex, branching filamentous networks as they multiply. They don't just float around as isolated single cells like a standard bacteria might.
Right, they link up.
Exactly. They form dense, intertwined mats. And as this biomass increases inside the bioreactor, the rheology, the actual flow behavior of the fluid changes drastically.
It gets thick.
Very thick. It transitions into a highly viscous, often non-Newtonian fluid.
It basically turns into a heavy, resistant sludge. A common way to visualize this kind of rheological nightmare is to think about trying to rapidly stir a giant vat of dense bread dough.
Or industrial adhesive? Yeah. The mechanical resistance is immense. You can't just swish it around. And that physical thickening of the environment leads directly to the core conflict of the brief, which is oxygen limitation.
Which is fatal to the process. Because these are aerobic organisms.
They need to breathe?
Exactly. They require a continuous high-volume supply of dissolved oxygen to sustain cellular respiration. That's what drives the metabolic pathways that actually produce whatever valuable biochemical we're trying to harvest.
Right, the whole point of the tank.
But as the fluid becomes highly viscous, the mass transfer of oxygen from the gas bubbles into the liquid phase just plummets.
Because the gas is effectively trapped, right? Or it just channels straight up the stirring shaft without mixing at all.
Precisely. The oxygen cannot penetrate that dense, intertwined filamentous network to reach the cells.
So you end up with a massive bioreactor full of highly engineered, incredibly valuable biological material that is essentially suffocating.
Suffocating in its own success.
Yeah, the system chokes on its own growth. The more biomass you produce, the more viscous the environment becomes, and the harder it is to keep that biomass alive.
And that paradox is the exact bottleneck.
Yeah.
The 7 to 10-day solution kit is designed to shatter.
Right.
And it does so by attacking the problem from both a mechanical and a thermodynamic angle.
Let's start with the mechanical. The first directive in the 7 to 10-day sprint is purely mechanical. The blueprint calls for the immediate replacement of standard Russian turbines.
Out with the old.
Exactly. Now, Anyone familiar with standard mixing knows a Russian impeller is going to create a high shear environment. It's this aggressive radial flow blade. But why is that specific shear profile a deal breaker for this type of fermentation? Why are the old blades failing so badly here?
It comes down to the physical structure of the microbes we just discussed. Those branching filamentous networks are delicate.
Oh, okay.
The standard Russian turbine operates by throwing fluid outward against the baffled walls of the tank. It creates these intense, localized zones of energy dissipation right at the blade.
Like a blender.
Very much like a blender. And in a low-viscosity fluid, that's great for breaking up gas bubbles.
Right.
But in a high-viscosity broth, forcing that aggressive blade through the dense fluid creates excessive shear stress.
Meaning the mechanical force required just to move the heavy fluid ends up physically tearing the biological material apart?
Precisely. You might succeed in mixing the fluid in that localized zone near the impeller, but you are shredding the fungal or actinomycete networks in the process.
Which is counterproductive.
Completely.
Yeah.
You are destroying the very cellular machinery you are trying to cultivate. The energy input is just too violent and too localized.
So the standard approach of just stirring harder fails catastrophically. You can't just brute force it.
No, you can't.
So the blueprint solution is to swap those out for large diameter hydrofoils, and it specifically cites max flow impellers as the standard. The explicit goal here is to increase axial flow without that excessive shear.
What's fascinating here is the shift in fluid dynamics. By moving to a large diameter hydrofoil, you change the entire flow pattern of the bioreactor.
Oh.
Well, instead of that violent, localized radial chopping, a hydrofoil acts more like an airplane wing or a ship's propeller.
Okay, I can picture that.
It generates a powerful unidirectional sweep of fluid straight down the central axis of the tank, which then hits the bottom and cycles back up the walls.
Oh, so it creates a top-to-bottom turnover of the entire volume rather than just spinning the middle layer really fast.
Yes. Because the hydrofoil has a much larger diameter, it can operate at a significantly lower rotational speed while still moving a massive bulk volume of that highly viscous fluid.
Right, it pushes more liquid per rotation.
Exactly. This low-speed, high-pumping capacity design generates the necessary bulk blending, that's the axial flow, while drastically reducing the localized shear stress that was damaging the cells.
That structural change makes a lot of sense. You transition from aggressive localized blending to gentle, full-tank circulation.
Right.
But solving the mechanical stirring problem only addresses half the equation, doesn't it?
It does.
Because you're no longer shredding the microbes and you're turning the fluid over efficiently. But if the fluid itself is still a dense barrier to gas transfer, just moving it around gently doesn't magically feed the starving cells.
No, it just moves the starving cells around the tank.
Exactly. And this is where the blueprint shifts to the chemical and thermodynamic interventions.
The mechanical overhaul prepares the environment. The next two steps manipulate the actual resources entering it.
Step 2 of the solution kit dictates implementing oxygen enrichment in the sparge gas. And the text specifies pushing the oxygen concentration up to a range of 25 to 40% O2.
Which is a massive jump.
Right. For context for you listening, standard atmospheric air that's used in basic sparging is only about 21% oxygen.
So by enriching the starch gas to between 25 and 40%, you are significantly increasing the mole fraction of oxygen in the gas bubbles being introduced at the bottom of the tank. You are fundamentally improving the quality of the resource.
But blowing richer air into a heavy resistant fluid still leaves us with a mass transfer problem. If the bubbles just coalesce into giant pockets and escape out the top without dissolving into the broth, all that expensive enriched oxygen is just wasted.
It's just bubbles right out the exhaust.
Right. Which brings us to the final and arguably most critical parameter change. The blueprint requires the use of a pressurized headspace, specifically up to 0.5 to 1.0 bar of pressure.
This is the thermodynamic linchpin of the entire operation.
And the blueprint explicitly states that the purpose of this pressurization is to increase the driving force, which it denotes with the equation C star minus C.
Yes.
Here's where it gets really interesting. I want to slow down and focus on that specific equation, C star minus C. Let's not gloss over the physics here because this is brilliant.
It really is.
Break down those two variables for us. How does 0.5 to 1.0 bar of headspace pressure directly manipulate that math to force oxygen into a viscous fluid?
Let's isolate the variables. In the context of gas-liquid mass transfer, C star represents the saturation concentration of oxygen in the liquid. It is the absolute maximum theoretical amount of oxygen that the fluid can hold under the current physical conditions.
The ceiling.
Exactly, the ceiling. Now, the second variable, C, represents the actual current concentration of dissolved oxygen present in the bulk liquid at any given moment.
So the difference between those two, the gap between the maximum possible saturation, C star, and the current actual level, C, that gap is the driving force.
That is the core mechanism. It is the thermodynamic gradient that compels the oxygen to move from the gas bubble into the liquid.
Okay, so if C is very low because the microbes are rapidly consuming the oxygen,
Yeah, and C star is high.
you have a strong driving force.
Right. But in a highly viscous fluid, the resistance at the boundary layer between the gas bubble and the liquid is immense. The fluid is pushing back hard.
So to overcome that severe physical resistance, you need a massive driving force.
Yes.
Yeah.
And you can't really lower C any further because the microbes are already starving. They've bottomed it out.
So the only way to widen that gap and increase the driving force is to artificially inflate C star, the maximum possible saturation limit.
Which is exactly what the headspace pressure accomplishes. The solubility of a gas in a liquid is directly proportional to the partial pressure of that gas above the liquid.
So by sealing the top of the bioreactor,
And pressurizing the headspace up to 0.5 to 1.0 bar, you are increasing the total pressure of the system.
and combined with the 25 to 40% oxygen enrichment in the sparge gas.
You dramatically increase the partial pressure of oxygen.
So by pushing down on the entire system with up to a full bar of pressure, you manipulate the thermodynamics to artificially raise C star.
You raise the ceiling.
You create such a high saturation potential that the oxygen is thermodynamically compelled to cross that resistant boundary layer and dissolve into the heavy dough-like broth.
It forces the mass transfer. The pressurized headspace basically acts as an invisible thermodynamic hand, shoving the enriched oxygen molecules into the liquid phase where they can finally be accessed by the cellular network.
That is incredible. Let's look at how beautifully synchronized this three-part architecture is. You have the large diameter max flow hydrofoils creating a gentle, full tank axial sweep.
Right, moving the bulk fluid.
This constant turnover continuously brings oxygen-depleted fluid from the depths of the tank up to the gas-liquid interface at the top.
Where the pressure is.
Exactly. Simultaneously, you have a 40% enriched oxygen environment under a full bar of pressure at that interface, creating a massive C star minus C driving force.
The hand pushing it in.
Yes. The pressure shoves the dense oxygen into the newly surfaced fluid, and then the gentle axial flow sweeps that freshly oxygenated fluid back down into the depths without shearing the delicate cellular networks.
It is an elegant closed-loop optimization. Every single intervention addresses a specific physical limitation of the high-viscosity state.
So what does this all mean? In terms of actual output, what happens after these 7 to 10 days of upgrades?
The payoff is substantial.
The blueprint outlines a quick win that results from this implementation. The first metric is a 30% increase in biomass density.
30%.
Achieving a 30% surge in cellular mass inside an already crowded industrial system in just over a week is a massive leap in yield.
It is a profound increase.
Yeah.
But honestly, it's the second metric of that quick win that truly validates the engineering here.
What's that?
The text specifies that alongside this 30% density increase, specific productivity denoted as QP is maintained at high cell densities.
Maintained. Not increased, but maintained. Let's dwell on the biological implications of that for a moment. Maintaining specific productivity, or QP, means the rate at which each individual cell produces the target biochemical does not drop.
Correct.
Why is that specific maintenance so remarkable when you increase the crowd by a third?
Well, if we connect this to the bigger picture of bioprocessing, biological systems are inherently self-limiting. Usually, as cell density increases, the environment naturally becomes hostile. Resources like oxygen become scarce, metabolic byproducts start to accumulate.
It gets polluted.
Yeah, and the cells enter a stress state, or what we call a stationary phase. They downregulate their metabolic pathways to survive.
They hunker down.
Exactly. So typically, if you force a 30% increase in crowding in a bioreactor, the specific productivity of the individual cell plummets.
Right.
You might have more total cells in the tank.
Yeah.
But each one is doing a fraction of the work because they're stressed.
Because they are starving. But here, the metric states QP is maintained. Every cell is still working at max capacity.
Which proves that the solution kit completely neutralizes the environmental stress.
Wow.
By optimizing the axial flow, enriching the oxygen and maximizing that C*-C driving force through pressurization, the bioreactor environment behaves as if it is infinitely resourced.
Even though there's 30% more biomass in there.
Exactly. Despite being 30% more crowded, the cells never perceive a scarcity of oxygen. They remain in an optimal metabolic state, continuing to synthesize the product at peak individual efficiency.
You essentially trick the biological network into ignoring the physical reality of its own density.
You do.
It is an absolute masterclass in removing a systemic bottleneck.
It really is a perfect case study.
Let's do a rigorous recap of the architecture we've mapped out today for you listening. We analyzed a blueprint for eliminating oxygen limitation in high-viscosity, non-Newtonian fungal or actinomycete fermentations.
And the intervention is a 7 to 10-day solution kit relying on 3 interlocking modifications.
First, we remove the mechanical violence. We replace the high-shear radial flow Rushton turbines with large-diameter max-flow hydrofoils.
This establishes a gentle, bulk axial flow that turns the heavy fluid over without shredding the delicate cellular filaments.
Second, we upgrade the resource itself by implementing oxygen enrichment in the sparge gas, raising the concentration to between 25 and 40%.
Right.
And third, we alter the thermodynamics. We apply a pressurized headspace of 0.5 to 1.2 bar.
This artificially inflates the saturation potential, maximizing that C*-C driving force to physically compel that enriched oxygen across the highly resistant boundary layer into the fluid.
The invisible hand.
The invisible hand, exactly.
And the resulting quick win is a 30% scale-up in biomass density while miraculously maintaining the specific productivity, the QP, of every individual cell despite the extreme crowding.
It's brilliant engineering.
It is incredibly satisfying to see a complex physical problem dismantled with such targeted precision. And looking at this framework, there is a broader operational philosophy here for you, the listener.
Definitely.
You don't need to be managing industrial fermenters to apply this logic. When a system you are running hits a wall and becomes sluggish or viscous, the instinct is often to either burn it down or just aggressively force things through.
Right, the equivalent of spinning a Russian turbine faster and tearing everything apart.
Exactly. But this blueprint suggests a much more calculated approach. It asks you to look at the flow dynamics and the driving forces.
Don't just push harder, push smarter.
Right. Sometimes you just need to change the geometry of how you agitate the problem to create a gentler, more structural turnover. And sometimes you need to alter the pressure of the environment to naturally force resources into the areas of highest resistance.
This raises an important question for us to leave on.
Let's hear it.
The most profound realization from this text is that resource starvation isn't always caused by a lack of supply.
Right.
It is often caused by an environment that has become too physically resistant to absorb that supply.
Wow, yeah.
So what is the high viscosity bottleneck in your current operations? And what specific combination of gentle axial flow and environmental pressure might be the 7-day solution kit you need to finally break through that resistance?
That is a fantastic lens to evaluate any project through. Thank you for joining us on this deep dive. We will catch you on the next one.
You've been listening to Biomanufacturing and Fermentation Technology with Prasad Ernala. Thank you for joining me. Until next time, keep engineering biology into reliable manufacturing.